Good morning to all. Welcome to the channel Firjan. So, electric charges and electric field. In this lesson, we discuss electric field due to infinitely long uniformly charged wire. So, about this we discuss electric field due to infinitely long uniformly charged wire. For that, this is the infinitely long charged wire. For this one, what we can discuss now first, linear charge density. Linear charge density means charge per unit length is called as linear charge density. Linear charge density represented by lambda, charge na q, unit length na L. So means lambda equal to Q by L is the linear charge density. For that, here in this infinitely long charge uniformly charged wire, why we are using this one linear charge density? It is infinitely long wire. So it is very difficult to calculate the electric field. So that's why we can use this one, lambda equal to Q by L. For example, unit length, 1 meter length, what is the charge density? Lambda. 2 meters, 2 lambda. 3 meters, 3 lambda. So that's why we can use linear charge density equal to charge per unit length. By using this, we can find the what is the total electric field due to infinitely long uniformly charged wire. For that, what we can do now first here, this is the infinitely uniformly charged wire. In this one, charge is distributed uniformly. So this is the positive charge. See, in this one, what is the electric field or distance from the wire? So r distance, what we can do now here, we can select Gaussian surface. We can draw the Gaussian surface. See, this is the Gaussian surface for infinitely long uniformly charged wire. What is the Gaussian surface now here? Cylinder is the Gaussian surface. That's why we can draw here cylinder or distance from this one. See, this Gaussian surface length is L. What is the length of this Gaussian surface na? L. In this Gaussian surface, charge will be distributed uniformly. Charge is distributed symmetric at every point. So symmetric means nothing but same. Charge distribution is same. See here, Gaussian surface should be symmetric about charge or charge distribution. In this one, see, due to this positive charge, electric field na, this is the electric field direction. See, positive charge na radially outwards. This is the electric field. See this one, this side, electric field is this one. See, electric field is this one. See here, this is the electric field. In this one, this electric field is find out by using Gauss law. What Gauss law na? The net electric flux through a closed surface is 1 by epsilon naught times charge enclosed by the surface. So that means phi closed equal to net flux through closed surface equal to Q by epsilon naught. Net charge enclosed by the surface, closed surface. Net charge enclosed by closed surface means inside the closed surface, what is the charge? Q in charge inside the closed surface by epsilon naught. This is the statement of Gauss law. By using this, what is the electric field due to this infinitely long uniformly charged wire? So we find out. For that, what we can select na Gaussian surface. This is the Gaussian surface. Cylinder is the Gaussian surface for infinitely long uniformly charged wire. This one, it has three surfaces is this here. What is the flux through this Gaussian surface? For that, this is the one surface, this is second surface, this is the third surface. Three surfaces is there. What is the flux through this surfaces now? First, total flux equal to pi 1, pi 2, pi 3. We can write. Means why? Because three surfaces. This surface, what is the flux through? This surface, what is the flux through? This surface, what is the flux through? We find out. For that, what we can do now here first, we can select small part. So small area we can select. Why? Because so Coulomb's law is valued for only point charges. So that's why we can here we can select small area. So this area we can select. See, in this one, this is the area vector. dA is the area vector. Electric field now here, this direction only, electric field is this one, E is the electric field. both are in same direction. So means what is the theta is the here not 0. Why? Because electric field vector and area vector both are parallel to each other. So same line, along the same line, so theta equal to 0. For example, this surface, see we can select this is the area, see this is the area vector dA, electric field vector, this is the electric field vector. What is the angle between this one? Theta equal to 90, theta equal to 90. So you select this area in this surface, this is the area vector, this is the electric field vector. See what is the angle now here now? 90 degrees. See what now? Theta is, theta is same at every point on the Gaussian surface. So means that is either 0 or 90. See here, here 0, here 90, here 90, this side na same 0. So means every point on the Gaussian surface theta is same. Theta is the angle between electric field vector and area vector. Theta is same, that theta is either 0 or 90. So this surface 0, this surface 90, this surface 90. So this is like what is the angle between area vector and electric field vector. See now we can write here what is the flux. See flux means here small areas na we can take here this one we can add, and what we get na integral. So flux formula is flux equal to electric field vector dot area vector. See E dot dA. So integral we can take, we can small. So that's why here we can write integral EDA, EDA, E dot dA. We can write this flux now here integral E dot dA. This one. See here 5 pi 3 integral E dot dA. This is the electric field vector, area vector. See here E dot dA means integral EDA cos theta. Dot product na here EDA cos theta. EDA cos theta. So this also EDA cos theta. Here see first one, first surface. Here what is the theta here? 0. Second surface 90. Third surface 90. See we can write here integral EDA cos 0. Here integral EDA cos 90. Here integral EDA cos 90. So this 0, this also 0. This is what now? See EDA cos 0. Cos 0 means 1. So we can write integral EDA. So remaining 2 is 0. See here total flux through closed surface equal to EDA. See we can write here electric field is same at every point on the Gaussian surface. That's why it is constant now. E outside we can write integral dA. Integral dA means for Gaussian means cylinder. What is the surface area now here? 2 pi RL. So that's why we can write integral A means, see integral dA means E into 2 pi RL. This is the area means 2 pi RL. So what we condition actually? Total flux or net flux through closed surface equal to Q inside by epsilon naught. What is the total flux here? E 2 pi RL. So I write here E 2 pi RL equal to what? Q inside by epsilon naught according to Gauss law. Q inside by epsilon naught. See E into 2 pi RL equal to Q inside by epsilon naught. Q inside now what is the charge inside now here? What is the length this one? L. So what is charge density? Linear charge density is lambda equal to charge per unit length. Length is L, charge is Q. So lambda. So lambda equal to what we can write here? Lambda equal to Q by L. So Q equal to lambda L. What is the charge inside this Gaussian surface na? This length is L, charge is Q. Q by L na. So we can get, so lambda equal to Q by L. So Q equal to what? Lambda L. What is the charge inside na? Here lambda L by epsilon naught. See here E 2 pi RL equal to lambda L by epsilon naught. This lambda cancel. What we get now here? E equal to lambda by 2 pi epsilon naught R. This is the electric field due to infinitely long uniformly charged wire. So E equal to lambda by 2 pi epsilon naught r. R is the distance from the infinitely long uniformly charged wire. Lambda is the linear charge density, means charge per unit length. So this is the electric field. E equal to lambda by 2 pi epsilon naught r. So lambda constant, 2 pi epsilon naught constant. What is the relation now here? Electric field is proportional to 1 by r, means electric field is increases, distance is decreases, distance increases, electric field decreases. So for that we can draw the graph now here. So along x axis we can take distance from the uniformly charged wire, along y axis we can take electric field. See here, distance is less na maximum electric field, distance is more na minimum electric field, means what now here, distance increases, electric field decreases. So this is the graph between electric field and distance or from the uniformly charged, infinitely long uniformly charged wire. This is the, what is the electric field due to infinitely long uniformly charged wire na? This is the electric field. E equal to lambda by 2 pi epsilon naught r. So E proportional to 1 by r. How the relation na? This is the graph for E versus a distance, E versus distance r from the infinitely long uniformly charged wire. See here what we can do now here. First, it is the infinitely long uniformly charged wire. For this we can select the r distance from the wire, we can select Gaussian surface. What is the Gaussian surface for infinitely long uniform wire na? Cylinder is the Gaussian surface. We can draw the cylinder, cylindrical Gaussian surface. In this one we can see this is the first surface, second surface, third surface. Here electric field lines, these are the electric field lines direction, means positive charge and radially outwards. We can find out what is the total flux through this Gaussian surface, which is equal to q inside by epsilon naught. That is the Gauss law. See, total flux through closed surface equal to net charge enclosed by the surface is 1 by epsilon naught times net charge enclosed by surface, 1 by epsilon naught times net charge enclosed, means q inside by epsilon naught. So that is, first we find out total flux for this surface. What is the flux? Pi 1. For this surface pi 2. For this surface pi 3. So for this surface, what is the angle between electric field vector and area vector na? 90. This also area vector and electric field na 90. So these two surfaces, so electric flux is 0. Why? Because perpendicular. So cos theta, cos 90 is 0. That's why this surface, flux through this surfaces is 0. Only this surface is there. That is E dot dA, cos theta. Theta is here 0. Why? Because electric field vector and area vector both are in same direction. So theta is 0. So E dA. E is the constant, means electric field is symmetric at every point on the Gaussian surface. That's why we can write electric field is outside constant. So integral dA. Integral dA means the surface area of the curved surface area of the cylinder. So curved surface of cylinder is 2 pi RL, E dot 2 pi RL. This is the total flux through this Gaussian surface. What this equal to? Q inside by epsilon naught. I write here E 2 pi RL equal to Q inside by epsilon naught. For Q inside we can do charge, linear charge density equal to Q by L. So Q equal to lambda L. Instead of Q we can write lambda L. So L cancel. So E equal to lambda by 2 pi epsilon naught R. So means what is the relation between electric field and radius, means distance from the infinitely long uniformly charged wire, all distance. So distance is less, electric field is more. See here, less distance, more electric field. Distance increases na, what na here, electric field decreases. So this is the graph of electric field versus distance from the infinitely long uniformly charged wire. This is the electric field due to infinitely long uniformly charged wire. This is very important for CBSE board exam. Yes, na? Now we discuss, next we discuss electric field due to cylinders. What is the electric field due to cylinders? See, once we discuss, we have two types of cylinders is there, hollow cylinder and solid cylinders. See here, we discuss first, we have two types of cylinders is there. Electric field due to cylinders. we can write here cylinders. See, cylinders we have two types is there. See here, one is hollow cylinder. Hollow, now here we have again two types is there, conducting hollow cylinder, and another one is non-conducting hollow cylinder. Non-conducting hollow cylinder. Here is now solid cylinder. So solid, now we have two types is there, one conducting and another one is non-conducting. Non-conducting, two types is there. See here, in cylinders, hollow cylinders or solid cylinders. Hollow na conducting, non-conducting. Solid na conducting, non-conducting. See here, in this case, how to charge distribution in these cylinders, that we discuss first. See, for example, here we have hollow cylinders is there, hollow, and one more is solid cylinders is there. In this one, conducting solid cylinder, conducting solid cylinder. See here, hollow na conducting and non-conducting. See here, conducting, non-conducting hollow cylinders, conducting solid cylinders. These two, what na here, charge will be distributed uniformly, but total charge will be resides on surface of the cylinder. See, charge resides on surface of the cylinder. On surface only it will be there, not inside. Inside is no charge, only total charge will be resides on surface of the cylinder. For example, non-conducting solid cylinder, non-conducting solid cylinder, what na, charge will be distributed whole cylinder, whole cylinder charge is distributed whole cylinder. But in case of hollow, conducting, non-conducting, conducting solid cylinder, charge will be resides on surface of the cylinder. Whatever the charge is there, it will be reaches to surface of the cylinder. So that is the difference between non-conducting solid cylinder, hollow conducting, non-conducting, conducting solid cylinder. So this, whatever the properties we are using for hollow, conducting, non-conducting, conducting solid cylinder, same. So for that we can use, we can find the electric field, one find out now, that will be related to all, we can find out. See, non-conducting, this is the difference. Why? Because charge will be distributed total cylinder, inside totally charge is there, but in case of this, charge will be on surface only, on surface only. Now we discuss electric field due to hollow, conducting, non-conducting, and solid conducting, solid conducting cylinders, solid conducting cylinder. Why? Because this all, these three will be, charge will be on surface, but in this one, whole cylinder is there. That's why this is one case, this is second case we can take. See, first we discuss electric field due to hollow, conducting, non-conducting, and solid conducting spheres. Electric field due to, now we discuss electric field. I write here electric field. See, electric field due to hollow cylinders. So hollow cylinders na here, conducting and non-conducting, non-conducting. Another one is solid cylinder, solid conducting cylinder. Solid conducting here, this we discuss first. Why na? This all will be same, charge will be on surface is there. That's why we can find for one hollow, we can find out. So it will be related to total. So means, so conducting, non-conducting, solid conducting cylinders. For that, what we can do now here na? So what is the electric field or distance? from center less than the capital R, one case, greater than capital R, another case. So means less than capital R means inside surface, greater than capital R means outside the surface. That two cases we can find out what is the electric field due to hollow solid conducting. So that we can find out. First case we discuss, or distance from the center less than the radius. See, for example, here we can take hollow, conducting, non-conducting, solid conducting cylinders. All will be, charge will be on surface only. That's why we can take, this is the cylinder, means cylinder. See, this is the cylinder. In this one, see, charge will be distributed on surface only. Here see, this is the charge, so distributed on surface. Whatever the charge inside is there, that will be reaches to surface only. Here see, positive charge is there, inside no charge. Why? Because solid conducting, non-conducting hollow, solid conducting cylinder, this all what the charge will be resides on surface of the cylinder. That's why. So means this case, see here, for this what we can do now, first case, so means or less than, or means inside the surface, inside the surface. See here, for that what we can do, or distance from the center, we can draw the Gaussian surface. For this Gaussian surface is for cylinder only Gaussian surface. Yes, na? See, this is the Gaussian surface. We can select the Gaussian surface. This is the Gaussian surface at all distance from the center. From the center. What we can do now first here? See, in Gaussian surface, charge will be distributed same. So Gaussian surface would be symmetric about charge distribution. Next, Gaussian surface, on Gaussian surface electric field is same every point on the Gaussian surface according to Gauss law. Next, theta is the same at every point on the Gaussian surface. So that theta is either 0 or 90 only. For example, see here, I can select this part, this one. In this one, what is the area vector na? dA. What is the electric field na? So electric field is E. So both are in same direction. For this surface, this area I select, area vector is here dA, electric field is dA. So means this direction. See what is the angle here now, 90. Here angle theta is 0. Here we can select this area now. So area vector is dA, electric field is this one. So what is the angle here? 90. So means here theta is 0 or 90, means theta is the angle between electric field vector and area vector on Gaussian surface. Theta is same or symmetric at every point on the Gaussian surface, either 0 or 90. See here, this surface 0, this surface 90, this surface 90. So this one. So now we find out what is the total flux through this Gaussian surface. And so by using Gauss law, we find out inside this R is inside the surface. That case, see what the formula here, phi closed equal to net charge inside the surface by epsilon naught. According to Gauss law, what is Gauss statement? The net electric flux through a closed surface is 1 by epsilon naught times q inside the surface, means net charge enclosed by the surface. That is flux through closed surface equal to q inside by epsilon naught. First we find out flux. What is the flux through this Gaussian surface? For that, see here, see in this one, it is theta equal to 0. So this one 90 na. So means what is the flux formula? See, E dot dA. So integral E dot dA. E dA cos theta. Here theta is 90. So means this case electric field is, sorry, flux is 0. Here flux is 0. Only we have this only. So that's why we can take here, see, integral E dot dA equal to q inside by epsilon naught. See here, E dot dA means E dA cos 0. Why not this one 0? This one 90. 90 is 0. Total flux is 0. Here also flux 0. We can take this one only. So means integral E dA cos 0 equal to q inside by epsilon naught. See, E is constant. We can write outside. So integral dA cos 0 means 1. So means integral 0 means curved surface area of the cylinder. So curved surface area of the cylinder is what na E 2 pi r L. What is the curved surface of the cylinder? 2 pi r L. What is the charge inside the cylinder here? Inside the cylinder or distance from the center inside the this one. So means inside the cylinder. See here, this one charge is always outside the cylinder on the surface. Means charge will be resides on surface of the cylinder for hollow conducting, non-conducting, solid conducting here. Inside this Gaussian surface, what is the charge? No charge is there. So means Q inside the Gaussian surface is 0. See here, here charge is 0 by epsilon naught. Means 0. So means E 2 pi r L equal to 0. Electric field equal to what? 0. So means electric field due to solid conducting sphere or hollow conducting non-conducting sphere inside or distance from the center, what is the electric field na? 0. Electric field is 0. So means inside or distance from the center, what is the electric field na? 0. So next, so what is the second case now? We find out r is greater than capital R. Means r is the distance from center, so that distance is greater than capital R. So means for example, see, this is the cylinder. See this one. In this one, what we can do now here now? See, or distance from the center, it is greater than capital R. Greater than capital R. This is the capital R. From center to this one is capital R. From this center or distance greater than means in this point we can draw the Gaussian surface. See, Gaussian surface is for this now. What? Cylinder is the Gaussian surface. It's not for this one. See, cylinder is the Gaussian surface. We can draw here Gaussian surface. This is the Gaussian surface. See, this is the Gaussian surface for all distance from the center. See, all distance. This is the all distance. See, due to this here, so cylinder, hollow cylinder, charge will be resides on surface of the cylinder. So due to this charge, what happened here? Electric field lines. These are the electric field lines. So means these are the electric field lines radially outwards. Radially outwards. See here, in this case also we have three surfaces is there. This is one surface, this is one, this is one. So due to that, so flux through closed surface equal to what? Flux through closed surface equal to Q by epsilon naught. Here Q means inside the Gaussian surface. Here we can draw Gaussian surface, that is all distance from the center. So Gaussian surface is Gaussian surface sphere is what here. So cylinder is the Gaussian surface, Gaussian surface, closed surface. So in this case, what is the flux through this Gaussian surface? That we find out. For this one, we can select small area. It is the area vector dA, and electric field vector same. In this case, here this is the area vector dA, field vector this one, electric field vector this one. So what is the angle here now? 90. Here we can take, sorry, not here, this is the Gaussian surface now. Here see this one. So it is area vector. It is the electric field vector. Electric field vector. See what is the angle here? 90. For this one Gaussian surface now. This is Gaussian surface. This surface here we can take. This is the area vector. It is the electric field vector. So what is the angle now here? 90. So this and this electric flux through this and this surface is 0. Why? Because 90 degrees. Electric flux equal to E dot dA, means E dA cos theta. Theta is 90. So cos 90, 0. This and this flux 0. That's why we can take this only. See, flux through closed surface now, integral E dA cos 0. Why? Because here theta equal to what here? 0. Electric field vector and area vector both are in same direction. That's why E dA cos 0 equal to Q inside by epsilon naught. E dA now here, E outside we can write dA cos 0. Cos 0 means 1. Integral dA means A. What is the area of the? Means EA equal to Q inside by epsilon naught. See here E. What is the curved surface area of the cylinder here? 2 pi RL. So that equal to what is the charge inside the closed surface? Means Gaussian surface, total charge. So what is the charge now here? Here total charge is here. See, q na, what is the charge inside the cylinder na, here q. So means here we can write, so 2 pi rl q by epsilon naught, q by epsilon naught. See E equal to what we can write na, so q by 2 pi r l, 2 pi r l epsilon naught, q inside na. So for that what we can write na, here see sigma equal to q by a, q by a. See E equal to q by 2 pi r l epsilon naught here na. So not sigma, c lambda. So lambda equal to what, charge per unit length. So q equal to what, lambda l. So means here instead of q we can write charge per unit length na. So charge equal to lambda into l we can write. So electric field equal to what na, here, so lambda l by 2 pi r L epsilon naught, L cancel, what we can write now here, electric field equal to lambda by 2 pi epsilon naught r, 2 pi epsilon naught r. This is the electric field due to hollow conducting non-conducting solid conducting spheres, solid conducting spheres. Inside the sphere is, inside the cylinder is zero electric field, outside the cylinder or distance na, that is lambda by 2 pi epsilon naught r, lambda by 2 pi epsilon naught r. See this one, inside na electric field is 0, where here or distance from the center, first means inside the cylinder, so that is electric field is 0. Outside the cylinder electric field is E equal to lambda by 2 pi epsilon naught r. This case E is proportional to 1 by r, E is proportional to 1 by r. We can draw graph now for this. See x axis we can take distance, this is r equal to capital R, this is r greater than capital R, this is r less than r. See we can take here na cylinder, see cylinder, so this is the cylinder, see this is r distance. So from, see here, from center to r distance, what na, here electric field is 0, so that's why it is along the axis is there. See from after means r distance outside the surface na, this is the graph. See this is the graph, electric field is proportional to 1 by r here, here electric field equal to 0, electric field equal to 0. This is the graph for electric field due to hollow conducting non conducting solid conducting cylinder. See inside the cylinder means hollow cylinder electric field is 0, outside the hollow cylinder E proportional to 1 by r. So means its electric field is decreases, means this is the E versus electric field versus distance r from the center of the cylinder. Now we discuss electric field due to conducting solid cylinder, conducting solid cylinder. See once, see electric field due to conducting solid cylinder. This is the conducting solid cylinder. See here electric field due to solid conducting cylinder. See in solid conducting cylinder, this is the solid conducting cylinder, what na charge is whole cylinder is there, but hollow conducting non conducting solid conducting spheres, solid conducting cylinders, charge is resides on surface of the cylinder. But in case of conducting solid cylinder, sorry, non conducting solid cylinder, non-conducting solid cylinder, charge will be distributed whole the cylinder. This is the charge. Charge is distributed whole cylinder. Again listen once. See, for conducting solid cylinder, hollow conducting non-conducting cylinder, charge will be resides on surface of the cylinder. In case of non-conducting solid cylinder, charge will be distributed whole cylinder. For this case, what is the electric field due to this non-conducting solid cylinder? Or small r less than capital R. One case, this is inside the cylinder. Second case, small r greater than the capital R, outside. It is inside point, it is outside point. Outside point. See here, what is the electric field that we want to find out. For that, what we can do now here, first see, we can select inside point. This is the center. From center to r distance inside the cylinder, we can select a point. This point, what we can do now here, Gaussian surface we can draw. For cylinder, Gaussian surface is cylinder only. So that's why here we can draw the r distance. See, this is the Gaussian surface for cylinder. See, inside point, this is the Gaussian surface for cylinder, inside point. See, this one, this radius is here, from here to here r. So from this radius is capital R. See, radius of the cylindrical non-conducting solid cylinder na capital R. At r distance from the center, inside point, at P point, what is the electric field? For finding that, we draw a Gaussian surface. What is the Gaussian surface for uh, cylindrical conducting solid na conducting solid cylinder na? This one, cylinder only Gaussian surface. That's why this point we find out electric field na. So electric field is symmetric at every point on the Gaussian surface. That's why this point some electric field is there. So here also same, here also same, here also same. So that's why we can find at P point what is the electric field, that will be same in the total Gaussian surface. So that's why we find out what is the electric field this point. For that, see what we can do now. Here Gaussian surface we can draw. This Gaussian surface should be symmetric about charge distribution. Charge or charge distribution. See, electric field at every point on the Gaussian surface is same, symmetric. The same way, theta is the angle between electric field vector and area vector. Theta is same at every point on the Gaussian surface. Either it is 0 or 90 only. So for that, what we can do now here, we can select some area. This one, electric field is, sorry, area vector is dA, electric field also this direction. See, both are in same direction. What is the angle now here? Theta equal to 0. We can select this one, this area. So area vector is dA, electric field is this one. See, what is the angle between this one? 90. So here we can select this point. It is the area vector and electric field is this one. See here, both are, what is the angle now here? 90. Means this case, electric flux is 0 through the Gaussian surface is 0. Why? Because flux means E dot dA. So here what E dA cos theta. Here theta is what? 90 degrees. So this value here flux 0, here flux 0, means pi 2 equal to 0 and pi 3 also 0. Only we want to find out pi 1. So this surface only we find out. See, what is the flux through closed surface, which is equal to what now? Q inside by epsilon naught. This is the Gauss law. What is the Gauss law now? The net electric flux through a closed surface is 1 by epsilon naught times charge enclosed by the surface, net charge enclosed by the surface. That we can write pi closed equal to Q inside by epsilon naught. What is the pi closed here? This surface 0, this surface 0, only this surface. That we can write integral E dA cos 0 we can write. Why? Because angle is the 0. So E electric field vector, A is the dA is the area vector. That equal to Q inside by epsilon naught. Q inside by epsilon naught. For this one, see, we can use new term that is called volume charge density. Why? Because charge will be distributed total cylinder. That's why we can write here volume charge density equal to charge per unit volume. Charge per unit volume. Charge equal to what here? Rho v. Rho means charge per unit volume, means volume charge density. So means charge per unit volume equal to, charge per unit volume is nothing but volume charge density. Charge equal to what? Density into volume. Density into volume. Now see here, EDA cos 0. EDA cos 0 means 1. So electric field is same everywhere on the Gaussian surface. So that's why E outside we can write dA. So means dA means curved surface area of this cylinder. What the curved surface area? 2 pi or L, that equal to Q inside. So Q means what? Rho into V. Rho V by epsilon naught. What is the volume of this one here? See this one. What is the charge inside the distance R from the center? What is the charge here? Charge is there. This charge is what? For that what we can write volume. What is the distance here? Smaller. So volume is what we can write now here? Rho. What is the volume of the cylinder na? Pi r square L. Pi r square L by epsilon naught. See what we get now here? E 2 pi r L equal to rho pi r square L by epsilon naught. This L cancel, R cancel, pi cancel. What we get now here? What is the electric field now here? Electric field equal to rho R by 2 epsilon naught. This is the electric field due to cylinder inside point or distance from the center. See what we can do now here. For that, first we can select or distance from the center point P. In this one, what we can draw? Gaussian surface. What is the Gaussian surface for cylinder now? Cylinder itself is the Gaussian surface. So we can draw the cylinder, Gaussian cylinder, this one. This Gaussian cylinder is the Gaussian surface. So for that, what we can do now here? What is the flux through this Gauss surface? That is pi closed and is equal to net charge enclosed by the Gaussian surface. So what is the net charge? Q inside by epsilon naught. For that we find out flux through this one. This surface flux is, so area vector this one, electric field this one. So theta is 0. So what here? Some flux is there. Here area, this is electric field vector, area vector, angle is 90. Flux through this one is 0. Why? Because EDA cos theta. Cos theta is here what? 90. Cos 90 is 0. That's why this side flux is 0. This side flux is 0. Only this surface only we can take. See EDA cos 0. EDA cos 0 means E is constant. Integral dA. Integral dA means E. dA means surface area of the cylinder 2 pi RL. That equal to Q inside. Q inside means charge density. Volume charge density equal to Q by V. Charge equal to rho into V. So rho into V na we write here. Charge inside the Gaussian surface is this surface. What is the charge? Rho V by epsilon naught. V means for this surface volume. So volume of this cylinder is pi r square L. This L cancel, pi cancel, R cancel. What we get now? E equal to rho small r by 2 epsilon naught. This is the electric field inside point P or distance from the center. So due to this solid non-conducting cylinder, outside point we can find out. Outside point means what here? Small r is greater than capital R. Small r is greater than capital R. See what that we can take. This is the cylinder. Yes, na? Cylinder means non-conducting solid cylinder. Charge will be totally is there. So totally distributed. Whole cylinder has charge is there. For this, from center or distance, we can draw this point. What is the electric field? We find out. For that, what we can do? We can draw the Gaussian surface. For this Gaussian surface is, see, or distance from the center. This one. See, Gaussian surface is, cylinder is the Gaussian surface. This is the Gaussian surface. See, this is the Gaussian surface. This one. So this is the Gaussian surface is the cylinder. So this one, in this one, what is the flux through this Gaussian surface? Equal to what? Flux through closed surface means Gaussian surface equal to Q inside by epsilon naught. Here see flux through closed surface now here. See this one. Area vector is dA. Electric field is E. What is the angle here? Theta equal to 0. For this one, electric area vector is dA. Electric field is E. So what is the angle here? 90. So means flux through this surface is 0. Why? Because flux na E dA cos theta. So cos theta means here 90, cos 90 0, that's why here 0. For this one, area vector is dA, electric field is E. So what is the angle now here? 90. Here also flux 0, here flux 0, here flux 0, here flux is not 0. Why? Because theta equal to 0. We can write here integral EdA cos 0 equal to q inside by epsilon naught. Q inside by epsilon naught. See here E is outside. Why? Because electric field is constant at everywhere on the surface, every point on the surface of the Gaussian surface. See here E integral dA cos 0 1. So we can write Q inside by epsilon naught. See E dA means 2 pi RL, curved surface area of the this Gaussian surface. What not? 2 pi RL. So that equal to Q inside. Q inside means volume charge density equal to Q by V. Q means rho V. So means here we can write instead of Q inside this one, this surface, what is the charge is there? That's one rho V by epsilon naught. So means V means what here? Volume of the cylinder. Volume of the cylinder. We can write here E 2 pi RL equal to rho. Volume means here capital R, capital R. So means pi capital R square L by epsilon naught. See this L cancel, pi cancel. What we get now here? E equal to rho capital R square by 2 epsilon naught R. Means what is the relation now here? E proportional to 1 by R. So means electric field is inversely proportional to R distance from the center outside point. Inside point, electric field is directly proportional to here. Electric field is directly proportional to R, means R distance from the center at point P inside the cylinder. So electric field inside the cylinder increases up to surface, outside the cylinder electric field is decreases. So for that we can draw the graph now here. See, this is the R, it is electric field on y axis. See here cylinder na, we can draw this one. So this is the cylinder. See here from R less than capital R, this case electric field is what? Directly proportional, means E proportional to R. So that's why we can write here E proportional to R, means electric field is increases up to surface. After that what happened now? E inversely proportional, so electric field is decreases, means electric field is inversely proportional to R. The electric field is directly proportional to R inside the cylinder. So means inside the cylinder is relation E proportional to R, outside the cylinder is E proportional to 1 by R. So means inside the cylinder from center to cylinder electric field increases, outside the cylinder electric field is decreases. So increases na here, see center to R distance, what na increases inside, outside R distance na it is decreases. This is the graph for electric field due to solid non-conducting cylinder. Solid non-conducting cylinder. Yes na, these are the conducting non-conducting cylinders. See, once we draw the graph again for conducting non-conducting, both we can draw. See, once I write here. See, for example, hollow, conducting, non-conducting, solid conducting, all will be same property. See, this is the y axis, this is x axis. We can take here x axis. Yes na, see, R distance, this is R equal to capital R. In this case it is R less than R, it is R greater than R. It is electric field along y axis. This case it is what na here? Hollow, conducting, non-conducting both, and solid conducting cylinder. Solid conducting cylinder, conducting cylinder. For that, what is the electric field? Inside the cylinder electric field is 0. Electric field is 0 inside the cylinder. After inside means after the surface of the cylinder, what happened now here? See, electric field is decreases, E proportional to 1 by R. This is the electric field versus distance R from the center of the cylinder. Inside is 0, outside is E proportional to 1 by R. For this is for conducting, non-conducting hollow, conducting solid cylinder. For example, see non-conducting cylinder. See here, this is the non-conducting cylinder. Non-conducting cylinder. See, it is R less than R, R equal to R greater than R. See, R less than the R, we discussed E proportional to R means from center up to surface, electric field increases. After center, what an electric field is decreases, E proportional to 1 by R. This is for non-conducting solid cylinder. Electric field inside is increases, outside is decreases. For conducting hollow, solid conducting or non-conducting hollow, what na? Inside is electric field is 0, outside electric field is decreases from the surface. These are the graph between E versus R distance from the center. So E versus R from center, inside outside point. Here this is E versus R distance from inside outside point. See, last problem, what na here? What is the flux? See, once I draw the diagram, see, for example, see here it is the x axis. For example, here see it is y axis, it is z axis. Here what na, here one rectangular surface is there. See, rectangular surface. See, this is the rectangular surface. Yes na? See here a solid, sorry, a infinitely long uniformly charged wire is there. Due to this uniformly charged wire, infinitely long uniformly charged wire, what is the flux through this rectangle A, B, C, D, that we find out. For that, see here what is the problem now? The flux due to infinite means or linear charged wire, infinite linear charge wire, due to infinite linear charged wire, uniformly charged wire, what na, the flux due to infinitely linear uniformly charged wire is flux through, sorry, through rectangle ABCD. ABCD is lambda L by n epsilon naught. Then find n value. We want to find out n value. See again, listen once problem. The flux due to infinitely linear uniform charged wire, uniform charged wire through rectangle ABCD, ABCD rectangle, how much flux is passes through this rectangle ABCD? What is the flux now? That is lambda L by n epsilon naught. What is the n value? That we want to find out. See, this is the infinitely long linear infinitely long uniformly charged wire, linear charged wire. So due to this charged wire, what is the flux through this rectangle ABCD? That we want to find out. For that, see here what we can do now. Here for example, see this is the infinitely long uniformly charged wire. So this is uniformly long charged wire na. So for this Gaussian surface is what? Gaussian surface is cylinder. So we can draw here cylinder. This is the cylinder, means Gaussian surface is the cylinder. See, flux what happened here? Flux is means electric field lines is outwards. See, normal like this. So means this is the electric field lines. See this like electric field lines. Here what na? Here this is the rectangle. So A, B, C, D. This is the rectangle A, B, C, D. What is the flux through this rectangle? That we find out. See, for example, this is the, for example, rectangle. See here, here infinitely uniformly charged wire is there. For example, see. So this is the infinitely charged uniformly charged wire. This due to this charged wire, flux is So means electric field length, this direction is there, this direction is there, this direction is there, upward. So means all surface, all directions is there. Why not here uniformly, sorry, Gaussian surface is cylindrical surface, like this is there, this one, this one, this one, this one, means 360 degrees. So electric field length is possible, radially outwards is there. So in that one, this one only, in this side, what are the electric field lines coming, that only entered into this rectangular surface, means ABCD surface. So that this case, what is the flux through this rectangular surface ABCD? That flux is lambda L by n epsilon naught. What is the n value? That we find out. See here, electric field lines like this, it is passes here, this process here, passes here. So this surface, how much electric flux is passes through this one? This is the rectangular surface. Here cylinder is there. This is the cylindrical wire, means infinitely long uniformly charged wire is there. For that we can draw the Gaussian surface. Gaussian surface is cylinder. Electric field lines is this direction, this direction, this direction. So downward. So means 360 degrees it will be passing the electric field lines. In that one, how many flux, how much of flux is passes through this one is that they give lambda L by n epsilon naught. But what is the n value that we want to find out? For that, see, this is the case. For example, see, here we can draw x axis, y axis is the z axis. Here this is the infinitely long uniformly charged wire. Here see, this is the rectangle ABCD. It is center is there. See, center will be at this one, origin only is there, like this is there. See what is the flux now here, distance between, sorry, one more point here, the distance between this wire is they give root 3 by 2a. What is the distance between infinitely charged wire with the x axis? Now root 3 by 2a. Here this length is L, this length is A. See again once, what now problem? See the flux due to infinitely linear uniformly charged wire through rectangle ABCD is lambda L by n epsilon naught. Then find the n value. For that, what now here we can do? See here, this is the infinitely long uniformly charged wire. For this we can select the Gaussian surface. Cylinder is the Gaussian surface. This is the actually rectangle. This is the rectangle. In this rectangle, what is the flux passes through this one is lambda L by n epsilon naught. This length is L and breadth is A. In this case, see what is the flux? Actually cylinder na. This is the cylinder, for example. Electric field lines downwards. This one, this direction, this direction, this direction, means every, means all surfaces is there, means 360 degrees it will coming. So what are the 360 degrees come now here? 360 degrees electric field lines are coming out. So in this one, how many field lines passes through this ABCD area? So for that, what is that they gave na lambda L by n epsilon naught. In this case, what is the n value? What is the n value? See, for 360 degrees, what is the flux na passes na here? See, for 360 degrees flux passes is q by epsilon naught. 1 degree na, see what na, q by epsilon naught into 1 by 360. Yes na? So 1 degree this one, how much we find out here, that angle? So automatically we can substitute one, we get the n value. For that, see here, this distance is root 3 by 2a. See here, so electric field lines passing na, here see electric field lines passing, so which makes like this is there, electric field lines. See this one, this length is from here to here root 3 by a. Why? Because this is the wire, this is the rectangle ABCD. What is the distance between them now here? Root 3 by 2a. So here this lines from this lines, so all now like this will form. See here root 3 by 2a. So this length is what? A. This length of breadth of the rectangle is A. So means here means center na, here this will be point is center is there. So means this distance is A by 2. So what is the angle here? We find out theta, we find out. So for angle theta equal to what? Tan theta equal to, we can take, so opposite side by adjacent side. What is opposite side here? Root 3 by 2a by adjacent side is a by 2. So 2 cancel, a cancel. What we get? Root 3. So tan theta equal to root 3, theta equal to tan inverse root 3. So means what angle? 60 degrees. Means 60 degrees angle, how many electric field lines is coming? That electric field lines is passes through the rectangle ABCD. Rectangle ABCD. For 360 degrees, how much flux through? Q by epsilon. Why? Because according to Gauss law, net flux passes through the closed surface is 1 by epsilon naught times net charge enclosed by the surface. That means flux through closed surface is Q by epsilon naught. Q means inside the charge. Inside the charge. Q by epsilon naught time. Q by epsilon. See, what is the flux through Gaussian surface? Now 360 degrees it will through the electric field lines. So 360 degrees equal to Q by epsilon naught. 1 degree equal to Q by epsilon naught into 1 by 360. What is here? What is the angle here? 60 degrees angle. What are the electric field lines coming? That only passes through the rectangle ABCD. So that means here 1 degree this much means 60 degrees means what we get? Q by epsilon naught into 360 into 60 na. So 0 0 cancel, 6 6 that means. So means 60 degrees. What is the flux now passes through here now? Q by 6 epsilon naught. Flux through closed means flux through rectangle ABCD is Q by 6 epsilon naught. What they give? Lambda L by n epsilon naught. Q means what here? Linear charge density, charge per unit length. So Q equal to lambda L. Instead of Q we can write lambda L. We can write lambda L by 6 epsilon naught. What they give? Lambda L by n epsilon naught. Epsilon naught cancel. Lambda L cancel. N equal to what? N equal to 6. What is the n value now here? N equal to 6. Means what is the flux through this rectangle ABCD na due to this infinitely long uniformly charged wire na 6 lambda L by 6 epsilon naught. 6 epsilon naught. This is the solution. Okay, thank you.